Welcome to the presentation of the paper Massive Wireless Energy Transfer with Statistical Channel State Information Beamforming. I am Francisco Monteiro from Instituto de Telecomunicações and also University Institute of Lisbon. This research, published in the IEEE Journal of Selected Topics in Signal Processing, is the result of a collaboration with Lopez and Alves that started during my sabbatical visit to the Center for Wireless Communications at the University of Oulu. Wireless energy transfer will play an important role in powering myriads of low-consumption sensors and other devices. While MIMO beamforming is known to be a key enabler for energy efficiency in wireless energy transfer, it requires full channel state information, which is difficult to acquire from these very power-limited devices. We are considering scenarios where the devices may appear in clusters. The MIMO channels are Rician, with a line-of-sight component and a Rayleigh multipath component. Because the terminals within the same cluster are physically close to each other, not only they share a similar path loss, but also the fading experienced by those terminals may be correlated, and that is the main assumption leveraging the proposed precoding schemes. The channel state information required from each cluster consists of the path loss, the Rayleigh fading correlation, and the line-of-sight components to each device. These slowly varying parameters are much easier to acquire than the instantaneous channel values. A central tool is to write the correlated fading component at each cluster as a function of the fading correlation. One starts with the known correlation matrix and, by applying the singular value decomposition, one obtains lambda and U matrices, which are two of the building blocks of H, together with an IID Rayleigh matrix representing the unknown fast fading. The energy harvesting circuits of the devices are modeled by a non-linear transfer function with both sensitivity and saturation thresholds. The problem is the one of maximizing the RF sum power available at all devices. For a single cluster, this translates to maximizing the squared norm of vector y. Considering this as matrix A, the maximum norm of y is attained when the transmit vector is the singular vector associated to the maximum singular value of A. Note that in doing this, one cannot assure that all components of that maximum norm vector are large, and in fact some can be quite low. This is the mathematics. The engineering here is to define this matrix A for more general problems, in particular the generalization to the multiple cluster case. We show that for the multi-cluster case, matrix A is a stacking of matrices describing the line-of-sight components of the clusters and the ones associated to the description of the correlation at each cluster. The solution also comes from an SVD now applied to this new matrix A. In order to guarantee a fair amount of power to all clusters, we have also defined a constrained version of the problem where the precoder tries to center the expected power at each device in the middle of the linear region of the harvesting circuits. Different transmission techniques were compared with our proposals. Here are the sum power distributions for several schemes and also the partial powers available at each cluster. While in the unconstrained solution one cluster gets a low share of the power, with a constrained solution fairness is attained. In this triplet of figures one can observe, firstly, the gain coming from knowing the fading's correlation, and secondly, the gain prompted by the rising of some line of sight. When the line of sight component gets stronger, the total available power increases and the variance diminishes, leading to a more steady energy flux as the channel becomes more deterministic. With an increasing number of antennas at the base station, the mean sum power grows linearly, however at the expense of a larger variance. The maximum mean sum power obtained via beamforming is found for a fixed position of the antenna array. Nevertheless, this value can be further increased via mechanical rotation of the antenna array. We invite you to check these and other findings in our paper, which is available in the IEEE Explorer, in our academic websites, and in the archive.